For more videos, visit forthesakeofeducation.com or support me at patreon.com/DaxterBells. Alright guys, let's do this problem where you have member AB is supported by a cable BC and at A by a square rod which fits loosely through the square hole in the collar fixed to the member as shown. Find the components of the reaction at A and the tension in the cable needed to hold the rod at equilibrium. So basically, you know that you have a tension obviously going that way, and you have reactions at A. Now at A we can slide up and down, so it's not going to have a reaction that way. It's only going to have reactions in the other two axes that are not the C, in other words the X and the Y axis. So we're going to have a reaction going that way and a reaction going that way. These reactions are not necessarily going in the directions as we've shown. When we find the reactions, let's call this one AX and let's call this one AY. When we find the reactions, if the reactions turn out to be negative, then you know they're going to be aiming the other way, the opposite way. So keep that in mind. So you know that in equilibrium, sum of the forces is equal to 0. That's the important thing to remember in statics. So what we're going to do when we have a problem like this, I like to do the Cartesian forms. Cartesian forms of all the forces acting in the system. When you find the Cartesian forms and you make a neat little table, then the problem becomes much easier to visualize. So how many forces do we have? We have the 200 Newton force right here. We have the 400 Newton force right here. And then we have the forces at A, AY and AX. We can put them in the same form, in the same Cartesian vector. And we have the tension, let's call it tension T. Equal. You could also put the 200 and the 400 in the same vector, that's not a problem, because they're acting on the same point. So the 200-pound force is going straight to the right, parallel to the Y. So it's basically Cartesian vector form is 0 in the I, plus 200 in the J, plus 0 in the K. The 400 Newton force is going straight down on the C, so it's 0 in the I, plus 0 in the J, minus 400 in the K. Now F of A, which are the reactions AY and AX, you know right off the bat that A cannot have a reaction in the C direction, so it's 0 because it slides on that rod. So we got AX in the I plus AY in the J. And then we have T. Now how are we going to do T? We have an I, a J, and a K component. This is how we're going to find them. You know basically that the Cartesian vector form of T is going to be T times a unit vector aiming in the same direction as T. Unit vector is a vector with magnitude 1 aiming on the same direction as T. Let's call it UT. How do we find this unit vector? Well, basically what we're going to do is we're going to find point B, then we're going to find point C, and then we're going to find the vector that goes from B to C. We're going to find its magnitude, then divide that vector by its magnitude, and that's how we find that unit vector. So let me find it in this second page. So we're going to find UT. To find UT, first we're going to find the points involved. Find points involved, which are B and C. Now as you can see by the graph, B sits at 3 in the I, plus 0 in the J, minus 1 in the K. And C sits at 0 in the I, plus 1.5 in the J, plus 0 in the K. So to find the vector that goes from B all the way to C, you basically do BC is found by doing C minus B. These are all vectors. And that is equal to minus 3 in the I, plus 1.5 in the j, plus 1 in the k. So now that we have the vector that goes from B to C, we got to find its magnitude. To find its magnitude, we do the x component square plus the y component square plus the c component square. So when you plug in these three values in here, you're going to get that the magnitude of BC is exactly 3.5. Nice number. So to find the univector BC, which is the same as the univector T because they're both aiming in the same direction, you basically got to divide the vector by its magnitude. So you're going to divide each of these three values by 3.5, and you're going to get that the univector has a Cartesian vector form of negative 0.857 in the I, plus 0.429 in the j, plus 0.286 in the k. So this is our univector T. Back to page 1. So what is the Cartesian vector form of T? Is basically the magnitude of T times each of the univectors, which looks something like this. Remember, our univector was negative 0.857 in the I times T, times the magnitude of T in the I, plus 0.429 times T in the j, plus 0.286 times T in the k. And you just copy the same thing up there. Negative 0.857 T in the I, plus 0.429 times T in the j, plus 0.286 times T in the k. Let me erase this thing in the bottom. You just copy it twice. So we have our nice neat little table. I love to build this Cartesian vector forms table. And you know that when you add them up, when you add them all up, they all come out to be 0, 0, and 0. So as you can see, you can build 3 equations right off the bat. So let's add the i's together. 0 plus 0 plus ax plus negative 0.857t is equal to 0. So the I tells us that ax minus 0.857t is equal to 0. The j, adding all the j's together and setting them equal to 0, tells us that 200 minus ay plus 0.429t, actually that's a plus, is equal to 0. And the k is a beautiful one, and it tells us that minus 400 plus 0.286t is equal to 0. So as you can see on our let's call this equation 1 and let's call this equation 2. On our third equation, we only have one variable, which is t, so you solve for t. T is equal to 400 divided by 0.286, I believe, and it comes out to be 1400 newtons. So that's t. And then basically what you're going to do, you're going to plug in t into equation 1 and then equation 2, and you're going to be able to solve for ax and ay with some simple algebra I'm sure you can do yourself. So ax is going to come out to be 0.857 times 1400. So ax comes out to be 1200 newtons. And ay comes out to be negative 800 newtons. When you solve for ay in the equation, you plug it in, you're going to get this negative 800. Now remember, originally I say that ay was aiming this way, and it came out to be negative. Since it came out to be negative, in reality, that just means that it's 800 going that way. AY is equal to 800 going to the left towards the negative y, newtons of course. That's what that means. So now that we found basically the reactions, now we have to find what's called the moment reactions. Let me make a new page for this. Moment reactions. So let me explain. Basically what you got to do to find the moment reactions, you got to find the moments that these forces cause onto A. So there's three forces, the 400, the 200, and the tension T that we found to be have a magnitude of 1400. Let me double check. Yes, 1400 newtons. So the first thing that we need to do is we need to find the moments created by these forces. So how do you find this the moment created by these two forces? You basically get this vector and you do the cross product with the forces. So the moment at A created by the 200 and the 400 Newton force is equal to, you do a cross product, I, J, K. Now let me write it here. The cross product will be the position of, let's call this point D. They didn't really give a name to this point, so D cross the forces, both the forces 200 and 400, we can put them in the same Cartesian vector. So the position of D is just 3 meters on the positive x and 0 and 0, and the forces are 0, 200 and negative 400. So what you do is you rewrite the first and second column, 3, 0, 0, 200. You do your positive diagonals. So I times 0 times negative 400 is 0, j times 0 times 0 is 0, k times 3 times 200 should be 600k. Now you do your negative diagonals. These are positive, positive, positive. Negative diagonals are, remember you have an extra negative sign, so the first one's 0, so it's 0. The second one has a 0, so it's also 0. The third one is negative times negative 400 times 3 times j. That will make it positive 1200 in the j. So that is the moment created by these two forces, the 400 and the 200. And then we need to find the moment created by the tension, because it's the other force acting on this assembly. So we need to find this vector, vector B. The moment created by the moment at A created by the tension is equal to basically point B cross the tension, the Cartesian vector form of the tension. Now there is a little slight problem, which is we don't have the Cartesian vector form of the tension yet, so we didn't really calculate it. So to find the Cartesian vector form of the tension, remember we know from before that the Cartesian vector form looks something like this: negative 0.857 times the magnitude I plus 0.429 times the magnitude J plus 0.286 times the magnitude in the K. And you know that the magnitude is equal to 1400 newtons. So all you got to do is basically multiply each of the coefficients by the t, and then you get the Cartesian vector form, which comes out to be minus 1200 in the I plus 600 in the J plus 400 in the K. So that's the Cartesian vector form of T. And that's basically what we're going to put in our cross product. IJK. First is the position of B. The position of B sits at 3, 0, and negative 1. You can see you go 3 towards the X and then you go down 1, and you have no magnitude on the Y, so that's why it's like this. Then you got negative 1200, 600, and 400. So basically we're gonna do the same steps. You're gonna rewrite the first and second column I and j. As you can see, I'm running out of space, getting in trouble. Minus 1200 and 600. And you do your positive diagonals, and then positive, 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 and then you do your negative diagonals in the same manner that I did the previous problem. And I'm gonna rewrite this here. Actually, I can slide down a bit. Hold on, that's better, more space. So the moment of A at t, I'm basically doing positive diagonals. The first one's 0, the second one is j times -1 times -1200. So that's positive 1200j. The third diagonal is k times 3 times 600, which is positive 1800k. Now negative diagonals. The first one has a 0, so it cancels out. The second one's negative times 600 times -1 times I, so it's positive 600i, sorry. And the last one is negative times 400 times t times j, so it's negative 1200j. Which is curious, these two cancel out, and this comes out to be 1800 in the k plus 600 in the I. And all you got to do is add those two moments together. The sum of the moments is equal to the moment that t creates about A and the moment that the 200 and 400 force create about A. So basically you're adding these, the k with this k, and the 1200 with nothing because there's no j component, and the 600. So the moment comes out to be 600 in the I plus 1200 in the j plus 2400 in the k. And those are the moments about the A that these two create. Just a little thought. Let me put a new page. This is something I wanted guys to show you. Pretend you have a block right here, right, and it's attached to a wall, and you have a force coming down, and I tell you find the reaction right here. You're gonna tell me that the reaction goes to the left, opposite to the original force. If I tell you that this force, for example, creates a moment this way, then you gotta tell me that the reaction will be the exact opposite at A. That's just something to keep in mind. The answer on the book is the one I showed you just now. However, those are the moments created by these forces. The reaction will be opposite. That's just something to keep in mind. However, this is the answer the book gives. So, final answer for the moments. Now let me slide back up. And let me see if I can find the page where I have the other answers. Right here. Here you have AY, and here you have AX. And you know that the tension, I'll remind you, is 1400 newtons. Final answer.
Please comment below if you want me to do any problems, and I'll be happy to help. Thank you.